joining and for your interest in the D2MS2 talk series. My name is Suparna Bhattacharya. I'm an assistant professor in the Department of Mechanical Engineering at IIT ISM Dhanbad. I am organizing this series in collaboration with my colleague, Professor Antarip Poddar. Antarip, would you like to say hi?
Hi.
Hi, nice to meet you too.
So our primary goal is to establish a knowledge dissemination platform supporting researchers interested in data-driven modeling for mechanical, fluid and thermal systems. And it's a pleasure to introduce our next speaker, Professor Olga Fink. Professor Fink has been an assistant professor at EPFL since March 2022, and she heads the Intelligent Maintenance and Operations System, IMOS laboratory. She is the recipient of an ERC Consolidator grant. Professor Olga's research focuses on physics-informed machine learning, multimodal learning, domain adaptation, generalization, and reinforcement learning for intelligent maintenance and operations on infrastructure and complex assets. Prior to joining EPFL, Professor Olga Fink was an assistant professor of intelligent systems at ETH Zurich from 2018 to 2022. And she was awarded the prestigious professorship grant of the Swiss National Science Foundation, SNSF. And between 14 and 18, she was heading the research group Smart Maintenance at Zurich University of Applied Sciences. She received her PhD degree from ETH Zurich and diploma from Hamburg University of Technology. She has gained valuable industrial experience as a reliability engineer with Stadler, Basang AG, and as reliability and maintenance expert with Proxys Switzerland Limited. She is serving as an editorial board member of several prestigious journals, including Mechanical Systems and Signal Processing, MSSP, Engineering Applications of Artificial Intelligence, and Reliability Engineering and System Safety. In 2019, Professor Fink earned the distinction of being recognized as a young scientist of the World Economic Forum. And in 2020, 2021, and 24, she was honored as a young scientist of the World Laureate Forum. In 2023, she was distinguished as a fellow by the Prognostics and the Health Management Society. And with this brief introduction, I would hand over to Professor Fink for today's talk. Professor Fink, the floor is yours.
Thank you so much for the kind invitation. Thank you everyone for joining. Thank you also for the kind introduction. It's really a pleasure to be able to share with you today some of our research that we have been working on in the past years, and to get your ideas and inputs as well. The title of the talk is a bit broad, but you will see what our interpretation of it is and what the approach to it is as well. But before I start with the presentation, I often first get the opinion. Yes, okay, now it starts working. So what I would like you to ask you is, what do you think is the biggest challenge in applying machine learning to engineered systems? So is it lack of data? Is it lack of interpretability? Is it violation of physical laws? Is it generalization? Is it extrapolation? Is it very long prediction horizons and the error accumulation that is associated with it? Or is there something else that I haven't listed here? So you can join by just scanning the QR code, or if you go on slido.com and type in the code of ML4E, then you will be able to participate. I give you some time to answer, so there is no one who has responded yet. I know it's late in the evening for you, but I still hope it activates you and makes you consider and then prepares you for the topics that I was planning to cover. So one person responded, the rest is has already fallen asleep. Okay, let's wait a bit more. Starts dropping in. How about the rest? Okay, let's start taking a look.
We have a response in the chat too. Piraj Mazumdar says lack of data.
Okay, so the 0 is not true actually. There was one respondent. So currently the majority is on lack of interpretability. Second is generalization, and then we have 3 that are just behind is okay, now it's changing a bit. So now we have 4 that have the same. We have very long prediction horizons now as well. And we have some who believe that it's extrapolation. So thanks a lot. It's interesting that you selected both of them to being equally important. Maybe have some different perspectives on that. Yeah, usually there is a clear favorite in one community, but maybe you're also a bit broader community as well. But thank you for responding. Okay, now it's generalization. Thank you for the additional vote. So my talk, what I wanted to cover with you today is how do we actually develop or integrate some of this or overcome some of these challenges that you just outlined are all important into our dynamics models for digital twin applications. And I explicitly want to go from physics to machine learning. And as promised in the talk title, I will also come back from machine learning to physics as well. So if we consider what are actually the attributes of an ideal dynamics model for digital twin applications, and actually there are the requirements that or the challenges that you just responded to are covered in this in these attributes here. So we have on the one hand requirements on the input data, or the challenges that we need to overcome. Obviously, we deal with noisy input data, but what we typically require as well is that we're just able to observe the trajectory data, and what we need to infer is, for example, the material properties or the evolution of the material properties without having any access to them. So this would be the requirements on our input data that we typically have limited knowledge on the input data, and it's typically noisy as well. Then we obviously have requirements on the generalization, and we distinguish in generalization, so generalization to unseen operating conditions. But we also typically have requirements on extrapolation as well. So this is when we are really outside of what we actually develop the model with or train the model with. So this would be a clear extrapolation regime, and it could be to unseen configurations or to unseen boundary conditions. And this is required if we really want to apply the model in a pure simulation setup. Then we obviously have requirements for the output, this long trajectory rollout. So if we really want to simulate, to use the model that we develop for simulation in an autoregressive rollout, so we really need to make sure that our errors are not accumulating. Otherwise, it's the model will be really useless for us. And we also need to provide dynamics really in a real near real-time manner. And as you also pointed out as well, everything that we provide to the decision makers needs to be interpretable as well. So I think we agree on those requirements and attributes, and let's take a look where we actually currently stand. So if we consider lamp parameter models, they are actually quite good in terms of the output, but obviously they are, we need to specify those already up front, so we cannot use them for parameter inference. If we apply them to something that we did not design or we did not set up them for, we need to recalibrate them or to redefine them again. Then we can go to finite element analysis or multiphysics simulations. They again quite interpretable, obviously. They're really good in long trajectory rollouts. They are computational quite heavy typically, and again, we will have difficulties to infer something that we did not specify and to apply them for the inference. And if we want to apply them to something else, we need to remesh them. We need to apply new boundary conditions and then resimulate the full models. And they are obviously data-driven models, including physics-informed neural networks as well. They are computationally quite fast at inference time. They're obviously less interpretable. They are accumulating error quite significantly typically. They are failing to extrapolate usually. Generalization can be limited as well. They're quite good in dealing with noisy input data, and they're also quite good in inferring something that has not been used as input for the models. So there's obviously quite some complementary, non-overlapping advantages of the models, and this is what has motivated researchers to integrate, to use the best of both worlds from them. And what I wanted to focus in my talk today is particularly on those quite difficult or quite challenging requirements and how we can actually achieve them and how we can overcome them. So noisy input data, so that is kind of given, it's what all of the models would be usually would be able to deal with, and also online dynamics is something that's particularly for data-driven models. It's not a very big challenge anymore, but it's still quite a lot of challenges when we deal with extrapolation, interpretability, but also long trajectory rollouts as well. And as most of you are familiar with, the field has been really moving into integrating prior knowledge and physics into deep learning models. And there has been this taxonomy on integrating different types of bias into the learning architectures. So we can either act on the input itself, so this is observational bias. We can act on the model itself, this is inductive bias, or we can act on the learning process and the loss of the objective function. So this would be the learning bias. And those of you who are familiar with physics-informed neural networks, I assume most of you, so this would be mainly on the learning bias. So we integrate the governing equations into the loss function, and this is how we train the models. Our research has been mainly focusing on looking into how we can integrate inductive bias into the learning architecture, because this is the strongest way to do it. But obviously also if we did not get it right, and if the inductive bias does not match the model or the real problem, then we will have also difficulties to generalize or to apply it to something. So it's the most powerful, but also we need to get it right in order to make it powerful as well. And one of the most obvious ways that we can actually use as an inductive bias is the physical connectivity or the interdependencies between observations or between components. And if we consider engineered systems, a lot of them can already be represented as networks or as graphs, such as, for example, the mass spring systems, even the bearings, bridges, but also sensor networks and water distribution networks, or in district heating networks. So we can already represent them as graph structures. And what we can actually do with them is that by observing how, for example, the masses move over time, that we would be able to infer the stiffness of the springs without having any knowledge on that. And this is could be still a simple system, but in the case of the human body walking, by observing of how the human body walks over time, that we would be able to infer the forces on the joints, for example, without ever measuring them. but just observing and learning the dynamics. And this is the main idea, that we're inferring changes by learning the dynamics and by indirectly having access to the properties that have not been observed and that are only available within this graph-based dynamical system. We could apply it, for example, to observing the wind turbine blade and then observing, inferring changes in the blade stiffness over time, but just observing the motion measurements. And this has been around really for quite some time. It's not a new idea. One of the ways to formally introduce it was by graph neural simulators, and the idea there is to define it as a message passing neural network. What we do in such a spring mass system, we define properties on the nodes. In this case, it would be the vectors of the position, the velocity. Then we define properties also on the edges as well. So here it would be the vector of the relative displacement and then the magnitude of the relative displacement. We define the graph connectivity that is given by this physical system here. And then we start encoding it, those node and edge features. So then we have the node embeddings that we do with simple multi-layer perceptrons, and then we have the edge embeddings as well. Once we encode it down, we can start processing the information. Let me move the video slightly. We can start processing the information. In this case, we are aggregating the embeddings from the nodes and then the embeddings from the edges. And then we start to perform message passing over several message passing steps. So it's in such a way that, for example, the node here also sees what dynamics was the node 3 experiencing as well. Once we perform this processing over several message passing step, we can start decoding. And again, for the decoding, we apply a simple multi-layer perceptron. In this case, we define the loss on the accelerations, and this is how we train the model over time. Let us take a look how it actually works on this simple linear mass spring system. So we trained it on 4, 5, 6, 9, and 10 masses. Now we apply it to 8, which is obviously out of training. And it works okay-ish. It does have some error accumulation, but it did learn actually the dynamics. But let's take a look how this model that we trained on this very simple mechanical system, how does it perform when we apply it in extrapolation setup. So now we apply it on 12 masses. As you remember, 10 was the highest that we used in training. And what you see now is that it starts deviating and behaving completely unphysically. So even in this very simple setup, it did not learn the underlying physics at all. So apparently this inductive bias is not sufficient. It's sufficient for interpolation, but it's not sufficient for extrapolation. And this is what motivated us to extend this framework and then to integrate additional inductive bias. So in addition to this pairwise relationships, we integrate additionally the conservation of linear and angular momentum, but also we interpret the message passing slightly as well. And this work was conducted by Veena Sharma, who is actually also an IIT graduate as well. So the framework, we gave the framework the name of Dynamical GraphNet, where the CAL stands for conservation of angular and linear momentum. And basically what the model does, it enforces Newton's third law at the level of internal pairwise interactions. And this is at the core of this framework. So in addition to the pairwise interactions, it also enforces this Newton third law, and we're not enforcing it at immediately at the level of the entire system, but at the level of pairwise interactions. And at the core of what enables us to do it is this antisymmetric local reference frame that we attach to each of the interacting particles, or two of the interacting nodes. And they are antisymmetric, and they are those local reference frames are etho3 equivariant and T3 invariant as well, which means that if we translate or rotate them anywhere in space, the properties that we compute on them remain unchanged. And this is really at the core what enables us to perform all of the steps that are introduced in this framework. And because those local reference frames remain unchanged, what it enables us to do as well is that we can take all of these vector features that we have defined, and then we can just project them onto the local reference frames, and then we just need to deal with the scalars of these projections because the local reference frames remain unchanged, so we don't need to take care of the vectors anymore. We just need to take care of the scalars. And this is what makes also the problem a bit easier for the architecture to learn. This is exactly what we do in the first encoding step. So we take all of the relevant vector features, and then we project them onto this local reference frames. And then we just take the scalars in the three directions from there. And then we encode them using simple multi-layer perceptron again. We encode the sender, we encode the receiver, we also encode the edge scalar features, and we also encode the node scalar features as well. Once we encoded the edge and the node properties, what we do is we start processing. So as you remember, we follow the same architecture, the same recipe as we had before for the graph neural simulator. So we have the encode process and we have the decode step. So in the process step, again, we aggregate the information from the sender and the receiver node, and then also from the edge scalar embeddings and the node scalar embeddings as well. And then again, we process it over several message passing steps. And then what we add as well is we add a bit of edge memory by providing information from the previous layer edge embedding to keep the memory of the past step. So once we processed it, we now can start decoding. So in the decoding step, we take the processed embeddings that we received here, that we obtained here, and then we can start decoding them. So again, for the decoding step, we use again simple MLPs. And we decode again just scalars because as you remember, we have this local reference frame, and then we take those scalars and then we multiply, and basically we scale the local reference frame with them. And because the local reference frames are antisymmetric, by definition, we conserve the linear momentum. Because they are antisymmetric, so it's really by definition, it's hard-coded that the linear momentum is conserved. So now we need to take care of the conservation of angular momentum. Here again, for the angular momentum, we use again a decoding MLPs to decode also the angular properties as well. So again, if we decode, again, by definition, the change in the angular momentum would be equal and opposite, and then actually the angular momentum is conserved as well. However, what we need to consider as well is we need to consider the contribution of the internal forces. And for that, we need to know what is the point of action of the internal forces. And for that, what we do is we take the weighted sum of the position vectors of the two connected nodes. And then the weights are just the node scalar embeddings. And by that, we obtain this point of action of the internal forces. And with that, we are ready also to compute the internal rotational torques as well, which are in this case non-symmetric. And with this, the angular momentum is now conserved as well. So now what we just need to do is we just need to update all of the properties that we had before. So again, We are decoding all of the interactions and the nodes, node updates to obtain the change in the linear velocity and to update the change or to obtain the change in the linear velocity and then the angular velocity as well. Once we have that, we can update now the current velocity as well. And with this, we can update the position. And for the position update, we use the single-step Euler integration. And then the loss function, this is very similar what we had before. However, what we add is a small adaptation with a regularization loss that we are not just predicting the current acceleration, but also the next time step acceleration that helps us with the accumulation of errors a bit. So just to summarize, what are the main features of this proposed architecture? So really at the core of why it actually works is this local reference frame that enables us to have it all the quantities that are symmetric, but also to conserve the linear momentum. So we have the conservation of angular momentum as well by considering on how the forces are updated and how the quantities are propagating. Then we have this encode process decode architecture with this forward time integration bias where we have this additional loss that we add. And there's one additional feature that we added in order to make the modeling easier and better adaptable to new boundary conditions. So for all of the boundaries, we add virtual reflected nodes. And to the reflected nodes, we attach the properties of the boundaries. And that we do for all of the particles that would be inside the simulated system. But then we only create an edge when the distance to this virtual reflected node is below the threshold. So in other cases, we don't touch them. But once a node is close to the boundary, we create an edge and then we treat the boundary in the very same way as we treat all of the other particles inside the system. So we just treat them as a different node type in this case. So let's take a look how it actually works in this simple setup where we had what you now see on the left is what you already saw before. So this is the graph neural simulator. On the right, what you see is our model. Again, it was trained on the very same data, and as you see, it actually is able to unroll over very long horizons and was able to capture actually the dynamics. With very long time horizons, it still starts accumulating error slightly. You may say it's a very simple system, and that's indeed very true. So this is why we extended the complexity. So now what we consider is we have a box with rough walls. In this box, we have 60 particles that have 6 degrees of freedom. And then we have 4 different cases where they start with different initial velocity and then they evolve under gravity over time. So now we don't just compare to graph neural simulator, which is one of the basic models, but also to more advanced models such as the equivariant graph neural networks, graph mechanics networks, and ClothNet, the conservative learn operator framework. And those frameworks are actually supposed to have some conservation or some equivariance integrated in them, or partly they are, such as the graph mechanics network, they're really adapted to those mechanical predictions. So we don't just compare to the simple baseline, but now also to the more advanced ones, and also for several of the evaluation, we add even some additional. So we trained the model on this 4 different cases with 60 particles, and we want now to evaluate, did it actually really learn something physical? So what we do to evaluate it, we take this trained model, then we apply it to 2 colliding particles. So they start with the initial velocity, then they collide, and then they repel again. So on the left, you see the simulated case. On the right, you see the prediction of our model. But obviously, we need to evaluate what is actually, if it's really physical. So what we took a look at is in different properties of this dynamic collision. So in this case, what you see is the kinetic energy of this collision. What you see in black is the ground truth. What you see in blue is graph neural simulator. What you see in pink is our model. And these other colors are the other models to which we compared it to. So it's still this model that was trained on the 60 particles. Now it's applied on just these 2 particles, and we wanted to evaluate, is it actually physical? So what you see is that our model is really able to follow the ground truth kinetic energy. Interestingly, the closest is actually the graph neural simulator, but it did not learn that it is a dissipative system. And all of the other models are actually really performing or behaving non-physically and really did not learn to replicate the physical behavior. We can obviously also observe the total linear momentum and the total angular momentum. So as you see, our model really conserves it, and all of the others did not learn to conserve it, even though they were actually supposed partly to do it. So now what we have is, so this same model that was trained on 60 particles is applied to an extrapolation regime. So now we have an initial velocity, we still have the 60 boxes, but it's now 3 times the initial velocity magnitude. So what you see here again is kinetic energy that we observe, and then the black is again the ground truth, and then the orange now is actually our model, so the color has changed. The blue one is still the graph neural simulator. It still behaves very kind of the closest to ours, and the others are again behaving non-physically. So we now wanted to evaluate how far we can actually go. So now we had this the model that was trained on the 60 particles. Now we want to apply it under very different conditions. On the one hand, we now change the number of particles to 2,000 or more than 2,000, and now we change the boundaries as well. So now we apply it in a rotating drum, and really we don't retrain it at all. We just apply it here. And what we do here is we apply it over 16,000 time steps, roll out in an autoregressive manner. So on the left, you see again the ground truth now in red, and on the right, you see our model. We not retrain just on the 60 particles. Again, we want to evaluate if it was actually behaving in a physical way or not. So now what we evaluate is the average slope in the XZ surface. And again, what you see, so this is over the rollout period, and it was actually evolving in a physical way. And obviously, it is a chaotic system. We cannot track the individual particles here. So just some highlights. It actually is able really to handle unseen boundary conditions. So in this rotating drum setup, it never saw this rotation before. It never saw that many particles. It's really is able to be applied in very long time rollouts in an in an autoregressive manner. And we model the boundaries in a meshless way, and this enables us to be quite efficient and really to model everything in the same setup. And just to emphasize here that we're actually able to apply it as a simulator, because we don't retrain the models. So what we normally have for surrogate models, that we need to train them on similar setups that we want to apply them to. But what we have here is that we can actually apply them in a setup where under boundary condition, under a setup that it was not trained at all. So it was trained on something different, but it's still following the same physics, but we're applying now as a simulator. We have some additional evaluations. We consider this constrained and body dynamics case where we have sticks and hinges, and the model is trained on one configuration, and we evaluate it on some others. So because it was actual results that were reported in a paper, so then we're reporting the same results. So it was trained on this configuration. And then when we apply it to the very same configuration, this is the performance. And then if we apply it to other configurations that it was not trained on, our model is still performing the best in this case, and with a big distance. But where it actually really shines is, so GMN was the best performing model, as you saw before. Where it really shines is where we apply it for several for rollout setups, and this is where most of the other models actually explode, and our model is still able to contain the error at a small level. And what is also nice that we actually don't need that many samples to train the model. So this is the training sample efficiency. So this is the number of samples that we use to train the models, and this is the prediction error. So the blue line is our model, and then we see the GMN, the CloveNet, the EGNN, and then the GNS. So our model is actually already performing quite well with just 500 samples. And the other models are not even able to reach it with 3,000 samples, which is still quite efficient. We evaluated it on human body motion as well, and again, our model was performing the best in this case. And interestingly, for this human body motion, what we added as well is a reflective node at the ground. So this is the last model that is reported, the performance of which is reported here with floor reflection virtual nodes, and this model was even performing better compared to the original, to the one that is not using this information. So the last two models are our models, and this one is specialized with the floor reflective node. And again, where it shines is when we apply it to rollout setups. In this case, the GMN was the best performing model, and it was not able to be applied in rollout setups. And we also evaluated the model on protein dynamic. So it's much larger system now, and the task was on predicting the positions of heavy atoms. In this case, interestingly, our model was not the best performing, so there was a hierarchical equivariant graph neural network that was performing better. It was really specialized and was using this hierarchical information. But when we applied it for the rollout and evaluated the error accumulation, so even though our model was not the best performing for one step ahead prediction, it was still performing very well on several steps ahead prediction. So these were the requirements that I started with for engineered systems. I hope I was able to demonstrate that actually this architecture using basic physical laws as inductive bias that are partly hard-coded, I was really able to fulfill most of them. We are able to extrapolate, we're able to generalize, we're able to infer additional parameters, because at every time step we can actually have access to all the internal forces. For example, we have very long trajectory rollouts, and it's actually fully interpretable because at every point in time we can check if it's still following the underlying physics or not. I actually prepared many more materials. I was asked to present only for 45 minutes, right? But maybe actually have also the closing loop. But just to share maybe some exciting results. By now, we adapted the architecture slightly. So now we apply it to fluid flows, and now we enforce conservation of mass, momentum, and energy by aggregating the fluxes, and we evaluated it on this well data set, on where a lot of other models were actually applied to evaluate it, and it's quite an extensive data set. So what you see here is kind of the distribution of the training setups, and we only trained it on just one data set. And then what you see here would be, this would be kind of the red ones would be extreme out of distribution, the green ones are still in distribution, and then would be the yellow one would be mild out of distribution. So we trained that proposed model on this setup, and this is the comparison models for that have already reported the results. So this is so our new model is the Flux GNN, as you see, our model is still performing, is performing the best in this setup. And what is interesting, so our model was only trained on one data set, and all of the others were trained on all of the data sets. So in distribution, and then out of kind of mild out of distribution, strong out of distribution, still performing reasonably well, and it's really able to generalize in this case. So these are just some of the visualization. This is for in distribution. This is mild out of distribution. And these are the visualization of strong out of distribution. And again, it's really different ways of integrating inductive bias. It needs to be aligned with the problem. It does improve the performance, but where it really shines is because we are able to apply it now in not as a surrogate model, but really as a simulator, and it provides improved generalization and extrapolation capabilities. We can fully interpret it and has very long prediction horizons. Before I end and don't cover the coming back physics part, I would like to thank the entire team. And if you're interested, we have been actually working on a review paper from physics to machine learning and back. We covered the inductive bias in one of the review papers, and then learning and observational bias in a second review paper. And we were actually working, the entire team was working on it, and it took us quite long. So if you're interested and have any feedback, so we'd be happy to receive them. I'm happy to take any questions, or if you don't have any, I can still cover the part that I was not able to cover.